A project operator eliminates columns, and this is another one where you have to be sort of careful about set versus bag. So when you see a projection in the set semantics, you're going to remove all columns that aren't explicitly listed, but you're also going to remove all duplicates that might remain. Okay, so if I project away all columns except for the last name, then you might think I get, Bob Smith and John Smith, and I get rid of first name, I'm left with two tuples or one tuple, right? Well, in set semantics, everything must be a set, and so duplicates get removed automatically. In bag semantics, they'll both be there. And if you write this query in SQL in any commercial database, what you'll get back is two tuples, both Smiths. You'll get duplicates, and then you can explicitly ask them to be removed with a different keyword called distinct. Okay, and we'll see an example of this. So as an example here is project social security number and names. We only want two columns out of all the original columns that might appear in the employee table. All right, and so here's an example of the set semantics versus bag semantics. Here's the original table with 3 columns, and we project onto name and salary, and so that means we get rid of SSN. Well, now we have 3 instances of a guy named John with 3 salaries, and the bag semantics would be okay with that. The set semantics would remove these, would remove one instance of this duplicate. And so the question here is which one's more efficient? Well, removing duplicates is expensive, so just leaving them in place is more efficient. And in fact, that's that's really the motivation as to why one of the key motivations why commercial databases assume bag semantics is that on every single query where you want to choose which columns you have, having an extra step to remove duplicates is sort of wasteful. In typical applications, you may not care, or you may sort of know by domain semantics that the remaining columns are unique anyway. Okay, so you can tolerate duplicates, and so forcibly removing them just to be pure with respect to the underlying semantics of the formalism was not particularly necessary. Okay. Okay. So an operator that you won't hear much about, but I do want to mention for a couple of reasons. One is that it's useful as a reasoning tool when you're thinking about manipulating tables, and then the other one is it actually is coming up more and more often in sort of analytics applications and data science applications. It didn't come up very often in traditional relational database applications, and that's this notion of cross product. And so a cross product here is for every tuple in R1, for every combination of tuples in R1 and R2, produce a tuple in the output. And so the size of this thing is the size of R1 multiplied by the size of R2 equals. Right? Okay. So fine. So an example where you might see this and why, sort of give you a flavor of why this is coming up more and more often is that you often want to find all pairs of objects that have some similarity condition. And while in any particular instance of this problem there might be tricks to do this more efficiently, the brute force method of just generate all possible pairs and then apply some function to determine their similarity is often used in practice. Okay. So for example, if you want to compare 2 images for similarity, right, you have 2 faces and you're trying to see if they're the same face, and you've got a piece of code that can do this. You now need to run. You have two big tables full of images, or just collections of images. Well, generating all possible pairs and applying the function is always a reasonable way to do this. Okay. So these kinds of operations are coming up more and more often, and I'm pausing because I was wondering whether to sort of mention briefly some of the techniques you can do to get around this, but I don't think it's going to come through very well without a little bit more visual aid. So let me skip that for now.